bar that's free to pivot around a fixed point like we did in class is a lever. An inclined plane with one or two slopes could be a wedge, so like the one you put underneath the door to keep the door open. A groove wheel with a rope, that's going to be a pulley, which we're also doing in today's lab, a pulley lab. The two wheels of different sizes, just like on your car, is a wheel and axle. And a sloping surface is naturally an inclined plane. Two wheels of different sizes that have the teeth locked together are going to be gears. We're going to be talking about that after you come back from the holidays. And then the inclined plane wrapped around a spiral, once again, is a screw. And the more threads you have on the screw, naturally the longer the plane, so the easier it is to put the screw in. So feel free to stop this at any time. If I'm not going to go down to classify everything as far as levers or inclined planes, there's actually only two types of machines. Those are levers and inclined planes. So under levers, you have a lever, a wheel, and axle. So think about the wheel rotating around, the axle being your fulcrum. A gear, once again, the center of the gear is the fulcrum, and a pulley, the center of the pulley is the fulcrum. Inclined planes, though, like wedges and screws, use a longer distance so you can use less force. Now, if you come down here, we discuss the ideal mechanical advantage. And if you remember, as a demonstration of an inclined plane, I had this ramp in class that looked like this, okay? And let's just say that the actual height that you went up was 1 meter, okay? But the actual ramp itself was 2 meters, okay? It says the mover uses the ramp to push a stereo into a van. The ramp is 3 meters long and it's 1.5 meters tall. I don't know why I just did the opposite direction here. But anyway, to get the ideal mechanical advantage would be the distance in over the distance out. Well, instead of using the ones I just made up here, let's go ahead and put in the numbers that they gave you. So let me erase this. Okay, so this is going to be 3 meters and 1.5 meters long. So this is 3 meters now and 1.5 meters. Well, the distance that you put in is actually 3 meters. In other words, the wheelchair or the ramp or whatever has to go up that ramp there. We're pushing a stereo, not a wheelchair. And the distance out, though, is actually only 1.5 meters tall. And so if you take 3 divided by 1.5, it should be 2 times easier. That would be the units for this, times easier. The thing is, though, it's usually not because of friction. So when I push, let's say the thing weighed 100 newtons, okay? Well, I should only have to use 50 newtons in order to push it up the ramp because it's twice as easy. But usually because of friction, it might be 60 or 70 newtons or even more than that. So that's why ideal mechanical advantage is the mechanical advantage we have when there's no friction. But the actual mechanical advantage might be a lot less than that. If you're doing a pulley, remember this from in class, we had a pulley system here, and we're lifting, I don't know, here's a block that we're lifting here. Well, the number of strings that pull up is your ideal mechanical advantage. So in this case, you have 1 string that pulls up on that. A screwdriver, if you look at a screwdriver, it's the width of the handle that is your distance that you put in. So the handle might be 4 times as big as the actual head of the screw. And so that's how you get the distance in, is by the radius or the diameter of the handle. And that's why with a little screw, you don't want to use a gigantic screwdriver because you'll end up stripping the screw. I don't know what just happened to my... Now, the next thing you'll need to know are these 4 definitions here. So input force is actually how much force that I have to put into the machine, what we call effort force. Output force is naturally usually the weight of the object or the resistance that the object is holding back on the machine. Mechanical advantage, I like the bottom definition down here best in the fact that it is the number of times easier. Oops, sorry about that. It's the number of times easier that a machine makes work. And the efficiency is going to be the work out compared to the work in. So you can never get more work out of a machine than you put in, because that would be disobeying the law of conservation of energy. So the ratio of work out to work in on a machine expressed as a percentage is your efficiency. So if I have a carpenter here that is trying to open up a top of a box, and he has to put in 500 newtons, and it takes 500 newtons to open the box, but he only has to put in 250. That means the mechanical advantage is going to be 2 times easier. Okay. Now that would be the actual mechanical advantage compared to the ideal mechanical advantage that we used before. Okay. Sorry, my handwriting's so bad. Now, if you look at the next part here, so what are the 2 ways that machines make work easier? Machines always are going to use a bigger distance so you can use less force, or they're going to change the direction of the force so gravity does some of the work. So, for instance, on a lever, you got a lever here. Attempt to draw that. If I got a lever here, when you push down on one side, the other side goes up. So if you're trying to lift something, it's always easier to push down with gravity because gravity's doing the work. So once again, how does a crowbar work? You push down with an effort force with gravity, so the resistance goes up. And then last but not least, what is ideal mechanical advantage? Once again, it's the ratio of distance input to distance output, or the number of times easier a machine makes work if there's no friction. Okay. So hopefully those worksheets will help there a little bit, and hope you enjoyed the show. Have a great day. Bye.